Welcome, everyone. Welcome to Austin, Texas, and thanks for showing up at our seminar. How are you all doing? Are you feeling it? So the agenda of our talk is how we built a relational database service in the cloud and what we learned from it. Do you ever wonder what happens when I step on the mic, okay. Do you ever wonder what happens behind the scenes when you deploy your database in the cloud? What goes in to keep these systems up and running so that you, as an application developer, can focus on writing a bug-free code? At Walmart, we had the opportunity to create this system from scratch, from the ground up. To date, we are managing thousands of servers in the cloud, in the private cloud, in the public cloud. And the agenda of this talk is to share that story, how we built that system from the scratch, and what to take, and everything around that. So are you ready? Should we get started? So the agenda is we'll go over introductions, get to know each us a little bit more. We'll talk about Walmart and what our team does at Walmart, the problem statement, and then our solution. But if at any times anything doesn't make any sense, please raise your hand so we are aware and I can probably find a slot to address those questions as we go. Introductions about myself. I'm Sandeep. I've been a Walmart associate for 5 years. At Walmart, my focus is mainly on distributed systems. And our office is in Carlsbad, California, which is 5 minutes away from the beach. And I'm a New England Patriots fan. I'm very excited to be here today.
Howdy, my name's Andre Van Looveren. I am a software developer at Walmart Labs as well. It's been about a year since I joined the team. Great culture there, I'll just mention. I have been doing software development for a great number of years. Most recently, I've been doing content management and even some front-end player development for an e-learning company. Fun fact about me, I play 3 outdoor sports every week.
Very cool. Now let's get to know you guys a little bit more, just to see what your background is. So by a show of hand, who here has ever used a relational database before? Outstanding. Who has experience with cloud environments? Okay, that's good. Who has used relational database in the cloud? Okay. Now, the last one is very tricky. Who is a Game of Thrones fan? All right. All right. So that helps a bit. So traditionally speaking, what picture comes to your mind when somebody says that they bought something at Walmart? A brick and mortar store, right? Or a physical store. But not anymore these days, because you can go to walmart.com and buy stuff using your laptop or any other mobile device. Walmart aims to provide the seamless omni-channel experience that tries to converge this digital and physical medias for shopping. For example, you can buy your stuff online and pick up at a store near you, or you can buy online, get it delivered to you, buy online, return at the store, etc., etc., etc. With 2.3 million associates worldwide and 75 million items sold online, with about 11,000 physical stores, solving problems at Walmart scale definitely pushes every system to its maximum. And in this talk, we'll focus on how we build the system and share the story with you. But before we go any further, we wanted to share a little bit about what our team does at Walmart. The name of our team is Data Foundation. And this is a very long, complicated mission statement. But the takeaways from this is we are trying to reduce the persistence complexity for application teams through common code, which is APIs, and by also managing data services. So what does that mean? Let's take a look at the products that we have in our portfolio. We provide persistence libraries, which provide simplified APIs for the application teams to perform gets and puts to different data sources. The data sources could be relational database, cache, streaming, search, and messaging. And we also provide managed services and tools on top of all these data offerings. And this is a picture of our team outing. We had an Office Olympics. And just for the record, everybody knows that me and Andre, we are Olympic gold medalists. All right, so back to the work. Let's focus on the work. What was the goal? What was the problem that we were trying to solve? So the goal was this. We were asked, hey, can you build an open source relational database platform that offers high availability, that we can recover in the event of a disaster, which has full lifecycle automation, and that is very easy for our customers to consume. But few things to note here are that the constraints with this requirement are that this requirement was given to us in a pre-container era, and at that time Kubernetes was still not considered stable for stateful systems. And Walmart at that time had access only to private data centers. So we looked at a few technologies. Few of them I have listed here. For example, we looked at MySQL Fabric. Fabric is a framework that manages a farm of MySQL servers, and it automates the high availability. We looked at MySQL Cluster. We also looked at MHA, which is the master high availability with MySQL. We also looked at Apache Helix. Apache Helix is a clustered management framework. We are trying to manage it ourselves with MySQL. And then we also looked at MariaDB with Galera Cluster. So we used various evaluation criteria for picking or selecting these technologies. The top on the list was high availability, or the RPO. One of them was RPO, recovery point objective. How much data loss is acceptable when we build the system? RTO, recovery time objective. How much time does it take to recover from an incident? How does the system perform? Is it cloud enabled? How much does this cost? Do we have to pay somebody for that? And there were other like killer cons we call, like is there a single point of failure? And any other like thing that we need to be aware that would make it like disaster architecture. So with all those things in mind, we came down with this result. We said, okay, let's go with MariaDB with Galera Cluster. So now that we know that's our go-to solution, let's take a look how we packaged it. So now we have some idea that how we came down to MariaDB. Now before we deep dive into our managed service solution, I just had one slide in case somebody here was not familiar with what MariaDB is. MariaDB is a fork of MySQL, and it was made by the original developers of MySQL, and it is an open source software. It provides a synchronous application between the nodes in the cluster. I took this picture from the MariaDB site, which shows 4 nodes. So all these 4 nodes are kept in sync by a piece of software called Galera. There's an active-active multi-master topology, and there's an automatic membership control, which means we can take nodes in and out of the cluster, and this piece of software called Galera will take care of replicating all the data between the nodes. All right, so now we know we have to use MariaDB with Galera. Where do we begin with? We thought the simpler design would be, let's have 3 nodes, 3 VMs, 3 separate VMs. We install MariaDB on each of the different nodes to provide high availability, because that's our first criteria for picking up a technology. So we provision MariaDB on 3 nodes, and if, let's say, VM1 or VM2, any VM goes out, that's taken care, the replication, the cluster is still up. So this bidirectional arrow in this picture, this represents the synchronous application that is offered by Galera. Then we thought, we need to expose these nodes to the application. So we threw a load balancer on the top. So the load balancer also took care of not just providing a connection string, but also of distributing the load between the 3 nodes. So next question was, okay, what happens if we lose a node? We lose a node, we still have quorum in the cluster because you still see 2 more nodes. So the cluster has quorum. So database is basically practically up. So we don't, there is no downtime for the application, but we are running at a reduced capacity. And 1 more node down can definitely compromise the cluster stability. But the good thing is, we buy some time, right? We buy some time to fix it. So we can fix it. We wrote some automation on top of that would fix it. And then, voila, we're back in business. So once the broken node or the VM3 comes back up, Galera takes care of synchronizing the data between all the lost updates from VM1 and VM2 to VM3. So that's good. So now we have 3 nodes on separate VMs, right? So how do we make the system further fault tolerant? So we thought, let's place each VM in a different availability zone or a fault domain, right? So different colors like the pink, yellow, and orange denote a different availability zone in a cloud environment. So that's making some sense, hopefully, right? Now we have 3 nodes placed in different availability zones. Now what could possibly go wrong? But remember, we only talked about 1 node going down, right? What happens if 2 nodes go down, or 3 nodes go down? Or what if we lose the whole region, right? So that led us to think there has to be something except just having 3 nodes beyond that. So which means we need a plan for disaster recovery, which was the second criteria, right? But before I move on, I'll take a quick question or two.
What were you using for your load balancer?
Yeah, so we use NetScalers, and one of the team built a software load balancer on top of it. They call it Torbet. And so the software load balancer it's called a global load balancer, but each data center had a physical NetScalers there.
So were you doing anything to try to send writes to only one of the Galera nodes, or were you just distributing everything?
That's a very good question. Can you hold on to this question? Because that's definitely one of the lessons learned we had. That will take the...
I would say it's not really a spoiler, but we were sending all traffic just round robin to all nodes equally.
Okay.
Yeah.
And yeah,
We'll learn later why you shouldn't do that.
yes, definitely.
That's a spoiler alert.
Right. Okay. So disaster recovery. We often think of this as a remedy for a physical disaster, tornadoes, hurricanes, floods, and fires. But a network outage, as Sandeep mentioned, of any significant duration, it can be an hour, 2 days, it's virtually the same thing, right? So since we have to have DR in place, we decided to explore what we could do to enhance our high availability, or our availability, and have a hot standby. We locate this hot standby in an entirely different data center, so it's unlikely to be affected by the traditional physical disasters, and hopefully less likely to be affected by a network outage as well. So with a hot standby, you've got a decision to make. Are you going to do this synchronously or asynchronously? Keep it in sync with your master. One of the considerations, of course, with synchronous is that this means that every single commit is going to take the hit of making the round trip to the other data center. And even for the closest regions, we were finding this is in upwards of like tens of milliseconds. And that was just going to be too expensive. So for that reason, we decided to go with asynchronous replication, which we do with a bin log replication. So this next question to ask yourself is, should this hot standby be a single node, or should it be a cluster? When we have an outage with our primary cluster, it may not be that it was CPU steal or a network outage or some other power failure. It can be that the application itself is not tuned properly, or the database isn't tuned properly, or the application is using usage patterns that are really just hammering the database. And if we're already struggling and then we failed over to a single node, the likelihood that that single node is not going to handle the load is quite high. So for that reason, we went with a symmetric topology here. So you'll see 3 plus 3 is actually what we ended up doing. An interesting thing to mention in going with a full-scale active and DR is that our backups are pretty much only used for point-in-time recovery. And for those who may not be familiar with it, point-in-time recovery is very helpful for when somebody issues that drop table, as was mentioned in the keynote earlier today, without the option for restoring the table, a delete that is missing a predicate and therefore deleting way too many rows. So that's what our backups end up being used for. The other thing that's interesting to mention is that when we fail over, because of the symmetry in the topology, we don't really care which data center is the active at any time, and we can run that way in an ongoing basis. All right, so now earlier I showed a picture of 6 nodes, 2 clusters having different roles, right? The active and the DR, and as well as now you have async replication between those clusters, so 2 of the nodes within each, or 1 node within each cluster also has a special purpose, right? And that's the async replication. So there's kind of a lot of stuff to keep track of, and that's necessary in order to orchestrate any change in that system, or to react with it for an outage. We need to also control which cluster is going to be accepting traffic. So we had to decide, how are we going to handle this orchestration? Are we going to have it centralized or decentralized? So really the question of whether to centralize it was found to be a no-go, because then it's a single point of failure. You know, if that system goes down, while everything's running, that's great, but events are going to happen. They're going to happen when you least expect it, and we don't want anybody to experience any availability loss. So if we were to decentralize it by just building in redundancy for that system, then we have this sort of question of how do we synchronize those various orchestration utilities, right? So that also comes with some complexity. So ultimately, we decided to decentralize our orchestration and decentralize the tracking of the roles for the different nodes. Oops. Oh, here we go. So we decided to go with a cluster local data store to keep track of the roles of the various nodes. To do this, we use Zookeeper. And just to be clear, Zookeeper, as you see here, is actually installed on every single VM. And it's a very small data store. It's really 5 pieces of data. It's the inventory of nodes on the active cluster, the inventory on the DR cluster, which one of the clusters is the active, and then which of the 2 nodes or hosts are involved in the async replication. We also, by doing this, you know, basically the VM should always be able to talk with itself. So we installed a Java agent, and that is using the information that's being tracked by Zookeeper to control a port, and that's the mechanism by which we allow application access to that database node. So it's basically just opening and closing a port based on what Zookeeper says, and also based on its ability to connect to the database itself. By closing that port, it actually tells the load balancer, hey, you know, stop sending traffic my way, if that's necessary, and that minimizes the, you know, the refused connections or socket timeouts when a node does go down, as illustrated by the dotted line in this node here. Let's see. Okay, so I've gone backward. That's no good. Sorry about that, folks. Here we go. All right, so this is just a completed picture of the entire assembly, inclusive of 2 clusters within different regions. And so it's fairly complex, but most of the concerns are managed at the local level by this agent. And just to be clear, that load balancer is also checking all the other nodes as well. So in total, it's going to potentially, although it would be a problem, direct traffic to all 6. So that health check is really important to make sure it's only going to the active and not the DR cluster. All right. So now let's talk a little bit about provisioning. We've sort of described our topology, but we haven't talked about how things get out there. We have hundreds of customers and a small crew to support them, so we need as many lifecycle events managed by customers as possible, you know, managing their own resources. So we built a self-service portal that we call Managed Services, creatively enough. This portal taps into OneOps. A whole separate group manages this, but OneOps is was purchased by Walmart in 2013, and among other things, it provisions and manages cloud resources. OneOps works with multiple clouds, and initially was used only for our internal or private cloud, and that was built on OpenStack. Today, we're also actively using Azure. And then the actual process of setting up our VMs is handled by Ansible. So when you go and deploy these things, okay, provision the VMs, and then Ansible's set up to get the agent out there, Zookeeper set up, populated with all the right data, so that the nodes, when they're stood up, they know what to do and how to behave appropriately. All right, so back to the managed services portal. Teams can provision their systems by simply logging in, specifying a name and size for the database, and what clouds they want their assembly deployed on. They can go to the managed service portal to also see their red, yellow, green status. And red, yellow, green is sort of an arbitrary thing, but it's basically a simplified way of showing the customers, application teams, the status of their database. So for instance, everything's great, you're green, a node, let's say, is down, that might be yellow. We're like on the precipice of failing you over, that's going to show as a red, and usually by then they're already aware that their tracking software is showing degraded performance. So we're usually already in contact with them by that point. Let's see. Another important thing here is that when they do their provisioning, they get a single endpoint for their data store as a URL, and you put that in a connection string. All right. I'll hand it over to Sandeep.
Right, so now we have a 6-node environment for one database, right? Active NDR. And what's the scale we are looking, or what, within like 2 years, we're looking at about 500 production environments. Each environment has 6 nodes, right? 1,600 non-prod environments that we are managing for this platform. And that comes down to about 8,000 computes in the cloud. And then we have a team size of about 10 people. That includes, this is a DevOps team, operations and engineering. So these numbers kind of created this picture in my head. I thought it would be funny to share. So what's the next logical question on this, right? How the heck you manage so many servers with a small team size and provide high availability for these databases? So with that context, I want to touch on the monitoring and alerting part. So we have different levels of monitors. We have a monitor on each process level, whether database on each VM goes down, or the Java agent that Andre talked about goes down, or each Zookeeper's process goes down. Then we have monitors at the virtual machine level, which tracks the various statistics like CPU, memory, and disk. But losing one VM or one process is not too disastrous, right? Because we have 3 nodes. That's why we have even monitors at the cluster level. What if I lose the quorum? What if I lose 2 nodes and there's a loss of primary component, which is the Kalera terminology for losing quorum? Or what if I lose all the 3 nodes? What if this async replication breaks down between the active and DR, because then your DR side is far behind the active? So we used the industry standard tools such as Nagios and Telegraph for collecting these metrics and monitoring all the systems. We also wrote custom scripts using Ruby and other languages on top of it, because there's always some gap, and then this is one of a system that we built just for our use case. We use PagerDuty for alerting. Yeah, so we get that call. We are used to getting those calls like 2 a.m. in the night, and we're like, the first thing is, oh crap, okay, let's wake up, fix it, right? So what's the next big thing then making a software? It's testing it, right? In fact, testing is so important that in so many software design philosophies, or what they call, give so much importance to test that is called test-driven development, right? But this isn't your typical application where you write a Java code, you have JUnit tests, or you write Python, you have a Python test, right? How do you test this system? The first thing is, how do you simulate that system? Okay, so we thought, let's use Vagrant VirtualBox to simulate the 6-node setup. But then how do you write those assertions, right? Hey, this is what I expected, and this is what I got. So we use Ruby to write a framework on top of this that would simulate a node down, node up scenario, and then we wrote assertions on top of that in Ruby. And there was another team at Walmart. Their focus was mainly creating a test suite for all of these kind of softwares. They use Play framework, which is basically a Java-based web framework, to do some tests. So basically, they had some REST APIs to like spin up a VM, make a node down. So we use that framework also for our testing. And I'll pass on to Andre for the lessons learned.
All right, so we've got the system provisioned, we've tested what we can, we've got monitoring in place, and what are the lessons learned? We've got a few here, so if at any time you have any questions or would like more details, definitely interrupt me now or at the end. Let's see, HA0, I realize after reviewing this, that's sort of a term we use internally. HA0 meaning high availability, 0 seconds. So a node goes down, nobody ever notices. You know, you'll get a few dropped connections, you know, in-flight transactions, for instance, but otherwise there's 0 time. You know, you talk to the load balancer, sends you to a new node, and you're still in business. Not everybody needs this. And the reason I mention that as a lesson learned is that obviously 6 nodes doesn't come free. You know, even if you have a database that's only 100 gigs, it's expensive. You know, disk being what it is, yeah, not everybody needs it. That said, there are some efficiencies to be had in both testing and automating that come from having the same topology everywhere. So if you're going to do it at that scale, you know, if you can find something that can be parameterized for teams, great. It wasn't something that we tackled. In the cloud environment, a node can go down at any time. This is one of those things that you know academically, and then once you get into it, it just bites you left and right. All kinds of different ways for things to go down, and it's very hard to simulate them all. Another lesson learned: if it's popular, your user base will grow very quickly, and you have to be prepared to scale. One thing I like to mention here is that DBA as a service, doing tuning, returning, scanning logs for folks, this isn't very scalable. So, if you can expose logs to Splunk or any other tools like that and empower your users, that's going to be really important. And then, can't overstate the importance of monitoring. Knowing before your customer knows is really critical to maintaining your reputation, and then just getting a jump on getting things fixed. Let's see. Automation can provide a high level of service and avoid scaling with people, but it's also, we would recommend that you log all the automated actions as well. And the reason for this is that if your database nodes are self-healing and they never tell you what happened, you're not learning anything from what's happening with your system. It can happen quite transparently, and it's going to be hard to make improvements after that. We actually found with some analysis that we did that some VMs within a cloud were much less stable than others. And as far as we were concerned, all the exact same hardware was on those VMs. If they were rebuilt, that condition may go away. And then you can also, because now we're multi-cloud, you can even compare the performance of one cloud to another, which is kind of interesting. And perhaps even engineer around that. Testing is really tough, as we mentioned earlier. One thing I'll just point out right now for you as a tip is that manipulating the IP tables can be really helpful for testing network outage. You can basically just swallow all TCP traffic. Make sure you don't also cut yourself off from that so that you can't get back in and reopen the ports. Let's see, creating one size fits all was very difficult. We were built around OLTP, and there were plenty of customers who really, in the end, wanted OLAP, and for that reason, they were requesting read replicas, and that was just going to be a departure from our topology and this sort of idea that it's easier to manage the same setup for everyone. Also, folks are using their database as a queue or a workflow engine, that's a contentious access pattern. And you'll see in a moment as I get into multi-master again why that's such a problem. So here's the biggest takeaway for today is that multi-master write comes with a lot of headaches. And what do I mean by that? Multi-master, of course, is just not caring which database node that you're connecting to and performing your transactions on. The reason this is a problem is that Galera, at least, uses optimistic locking. And so what that means is you may go through your entire transaction and up until the point you go to commit, and everything looks great. And if that database node were in isolation, your commit would be accepted, everything would be great. But it's not until you issue that commit that it checks with all the other nodes to see if that can be committed on the cluster as a whole. And at that point, you can actually fail. So if you're not prepared to reissue all of your statements, basically recreate that transaction, that can be a problem. It's basically a loss. And so many clients weren't really ready to do that. And the performance implications when these kind of rollbacks are performed frequently can be quite great. Another something that comes to mind with respect to multi-master is that bulk transactions have to be limited. The number of rows affected and therefore need to be moved around to all the other nodes can have an impact on your eventual consistency, which I'll touch on in a moment, as well as your transaction rate. So if you got a lot of transactions coming in, your time to consistency across the nodes increases. So this last point I have here is that write concurrency is actually lower when you access just single node for writes. That may sound counterintuitive. This idea of, oh, let me distribute the work across the 3 nodes is like, oh, great, I've got more horsepower. But each write that's happening in one place has to be replicated elsewhere. So it's really triple the work. And you're not really buying yourself much there. And actually, the overhead, oddly enough, of distributing the writes is much higher than sending all the writes to one node that then get sort of, I'll say symmetrically, if that's the right word, sent to the other nodes. So we did some sysbench testing, and where we maxed out with 700 threads doing this multi-master write scenario through the load balancer, we were able to get upwards of 2,000 threads going simultaneously, even though we're hitting the cluster via one node as the master for writing. So you could look at that as perhaps a 3x improvement, but it was just plain as day. The performance was much better isolating writes at least to a single node. So I did want to touch on the eventual consistency too. This was a huge problem for many of our application teams, many of whom were doing things like workflow and queues. And the reason for that is if they're not using the same connection to read what they just wrote to the cluster, they can get stale reads essentially. It's not stale reads in the classical sense of the word, but it's just if I write something to VM1 and then I'm trying to read it from VM2 just by virtue of having a different connection, whether that's in a pool or just newly established, there's a 2 in 3 chance I'm not going to be reading from the node that I just wrote to. And that was a big problem for many customers. So what do we do about this multi-master write? We've got this load balancer in place. It's there for a reason. Gives us robustness across nodes going down. Our solution was to use a feature of the connector.j JDBC MySQL driver, which is its failover scheme. And this is the default scheme. So if you have a connection string that says JDBC MySQL, what's kind of not there explicitly after that second colon is a failover. What that allows you to do is actually list multiple hosts, and this feature is amazing. Every connection will go to host 1 by default. Should host 1 be unreachable, down for any reason, or just not accepting connections, maybe you hit max connections, connections will start to be established on host 2. And this is done transparently to your code. All right. What's even more fascinating is that if you are connected to host 2, the driver itself will check host 1 and migrate your connection back to host 1 when host 1 becomes available. The reason that that's so important is, consider this. You have a situation where host 1 goes down, and actually, you know what? Let me illustrate it. Here we go. Here's our topology. We're connecting to host 1, and everything's great. You know, all the clients are connecting to host 1, things are great, and then host 1 goes down. Connections start being established at host 2, and that's wonderful. But if host 1 comes back up and new connections are made on host 1, now you've got connections going to 2 hosts at the same time. And then we're back to the headaches of multi-master writing. So fortunately, it's very aggressive. That's not very aggressive. I'll come back to that in a moment. But the driver will migrate your connections at transaction boundaries back to host 1 when host 1 is reestablished.
So when you're creating that connection string, do you just list the databases in your first cluster, 1 through 3, or do you go 1 through 6?
Yeah, so great question. And we actually list all of the hosts. What's really great is, as long as you're very tight on which hosts are up at any time, if host 4 is the first one that it's able to connect to, that's fine. There's almost the performance degradation of checking host 1s, 2, and 3. If you set the other connection string parameters properly, like socket timeout, for instance, is very minimal. And then if you're using connection pooling, that overhead or delay is going to have been, that performance hit has been taken offline, essentially, right? So yeah, we actually do recommend to our customers that they use all 6. And the reason for that is, if we do a failover, they don't have to change their configuration of their application nodes. So if it's just we've gone down for infrastructural reasons, or they've done something to us that causes the databases to go down, they don't necessarily have to change anything. And in the matter of a few minutes that we fail them over, they're back up and running without having to do anything. Another question? Sorry, can you repeat that?
You have a 3 active master, right? If you only use 1, right? It sounds like 1 master, 2 slaves.
Okay, yeah. So the question is, how is the Galera cluster different than having 1 master and 2 slaves? And what I would say to that is, that may not be that different. The Galera cluster. Galera cluster advertises their functionality as virtually synchronous, and so the degree to which they're synchronous is higher than if you were doing traditional async replication to the slaves. I mean, like the delay is usually in the order of microseconds, if not just singles milliseconds. By which I mean, when you hit say commit, and you get the response back at the application level that says, hey, your commit was accepted. Great. That means that certification passed on all the nodes. The write set that's been sent out may not have been applied to the other nodes, but that's going to happen really, really, really fast. And that delay, if it's important to you, is going to be much better with the Galera.
I'd say another big benefit with Galera is you don't have to do anything to promote one of the other nodes to be a master. If there's any, yeah, so they're all equal. You just choose which one is your node that you're writing.
Right. You basically got bidirectional replication across any pair, and that's great because it takes some of the complexity out. I mean, it's already a complex enough system, and it takes some of that out for us. Right. Right.
In the JDBC connection string, you are mentioning server 1, 2, 3. But if the server 1 is alive, always connections will go to that server only, right? You are not taking advantage of all the servers in the cluster.
Correct. Yeah. So we actually have sort of a hybrid approach that we even recommend, that if a team can accept EC read, eventually consistent reads, by all means use the load balancer, or they can do a hybrid approach where they're doing all writes and IC read needs, immediately consistent read would use the 1 connection string, and then have a second connection pool with its own configuration to do the EC read pattern.
Have you talked to any of your customers, or have you worked at all with your team with the WS rep sync weight variable?
Yeah, so we also explored that. for the sake of time, we sort of eliminated like all the different things that we discussed and even did proofs of concept for. WS rep sync weight was one of them, even if it was just set to 1, which would just do serialize the reads, and the performance impact was too great. For people who were already having, or application teams that were already having problems with contention and rollbacks, it just killed their performance. It was really bad.
Did you test a permutation where you sent all writes to one node and then sent like consistent reads to other ones that use WS rep sync weight?
Being a platform as a service team, we try to push as little of the responsibility onto the application teams as possible. So they're free to go and set that in their configuration or set it at the session level if they want to, and we're happy to advise them on that. But ultimately, we didn't want to sort of push teams that otherwise wouldn't have explored that into that, because there are a lot of permutations for that, and it could get complicated.
So only one thing I would like to add is that we started with this, that it is fully synchronous. Then we came down, oh, it's virtually synchronous. After 2 years, we realized, no, it's eventually consistent.
Sorry, I had one more image on this, and it was just to demonstrate that, yes, when we take out, let's say we've got a compromised cluster here, node 1 has gone down, by virtue of listing all 6 nodes, we do have this scheme happening, again, automatically out of the gate, just by using the MySQL driver. And I say just by using the MySQL driver, but truly there is a corner case that isn't handled by the MySQL driver, and internally Walmart has actually patched this, and hopefully will contribute it back to the community soon. And I'll tell you the details later if you're interested. Just a few things to wrap up. I think we're running out of time here. Here's a slide to highlight some of the technologies that we're using. And I guess let's move into any further questions.
So how are you handling the DDL operations in the cluster?
Yeah. Okay. So DDL. Do you wanna do that one?
Yeah, I'll do the hard one. Yes, DDLs we found interesting that because anytime you run this alters on a cluster system, it kind of halts the performance. I mean, you cannot run your DDLs while there's traffic going on in the cluster. So we took 2 approaches. If you're an application, if you're like back-end processing, and if you can take downtime, then the recommendation is that, yeah, you run your DDLs and take a downtime, right? Maybe run it at the night time. But then, because this is a managed service, right, and there can be different use cases, there were other customers who were very online and they could not take any downtime, I mean, very minimal. So for them, we recommended use online schema tools, like Percona's online schema change tool. Even that, because even that, you rename, that works in a way of renaming tables, has a copy of the table, moves all the data, right? But towards the end, there's that rename table statement, which is going to like wait, everything beyond, after the rename is going to wait to the rename. So there will still be a point of time where you will have like, you won't, I don't know what's the time, it's milliseconds or time when you kind of won't, there will only DDLs running on the system cluster, not the live operations. So
It was like sub-second.
Sub-second.
The rolling schema upgrade, isolation level?
Yeah, we did not try that. I think, why didn't we not try that? There was a reason.
I'm drawing a blank.
Yeah.
I should find that out.
Yeah, we should find that. I think we looked at it like maybe it was the automation. I think it may, because imagine this is not, we don't have any DBAs, right? This is all through automation. So we have to also look at like how can we provide a solution, right, which is automated. So maybe at that time it was quicker ROI giving PT Online schema change tool than investing, I don't know, 3 months building this automation. So maybe that's the reason.
Just a question, what cloud service do you use?
Cloud servers?
Yeah, what cloud service do you use in the database? Do you have your own cloud?
Oh yeah, so Walmart, we started with private clouds. Walmart had its own private clouds. So the way they handle availability zones there were they had sub-clouds they used to call. So we use private data center at the time, but we can also deploy this in Azure today. We just need to provision. So the way, like Andre mentioned, there's a portal, OneOps. That's a company that Walmart bought, I think, 3-4 years ago. What it does is it uses this OpenStack and other APIs to provision VMs, to carve out VMs from the cloud. So that's by default to us as an input that we get like 6 IP addresses of a VM, and then we start provisioning things on that.
Yeah, question. I saw your cluster is going to be like 5,000 computes with, I'm guessing 5,000 databases. Once, and your team is only 12 people. Once you build this, after 2 or 3 years, you need to either if you are running on Red Hat, you have to completely upgrade the OS or migrate it up, patch the database. How are you doing those functions equally?
Yeah.
Patching, upgrade, and the whole stack.
Right. So you mentioned patching and upgrades. So we wrote also automation on top for upgrades. So we track all releases, like let's say we release 1.0. So that's tracked within a VM. On a VM, we have a file that tracks the version number of these. And then we also wrote an automation on top of that. So if we release, let's say 2.0, so we are very much aware, like what are the differences? Is that, can we really upgrade this in a rolling fashion? So like the way, Ansible. The way Ansible work, maybe make it work, is that we do rolling upgrades on our servers for our software. But I think if you have to upgrade the database, so that's a separate story, right? Because you have to make sure, is the database compatible with this rolling schema upgrades? For example, today we are on 10.1. If we need to go to 10.3, then we cannot just do rolling upgrades. Because there, at that time, we need to have a release that provides 10.2, 10.1 to 10.2, then 10.3, right? Or like if a team can take a downtime, then we can recommend that, hey, you just migrate. Like, for example, there are other variables you mentioned, like the operating systems, right? So even for a new operating system, we need to have a new release that we need to certify that this software works. And I guess for that, the path at this point is just migration.
So who will migrate? You have a team of, because if you're 12 people will not be able to migrate
Yeah.
500 databases.
So for one cluster to other cluster migration, we also wrote a piece of software that does this migration. So you can still have traffic coming to your active cluster, which is the active and the DR side. We build provision new system, right? And then we take a backup from the original one, restore on the new cluster, and then we build an async link again to the new cluster also. And then we let the application team confirm, hey, do you think this new cluster is consistent with what your old one is, and what's the best time to cut over? All right, so we have 1 minute, so and we can answer more questions after.
Well, I guess one thing I was wondering, so at the beginning, you said you considered these 4 different things, and you decided to go forward using MariaDB Galera cluster. And at that time, maybe you thought it was a synchronous replication solution, and then maybe it's a virtually synchronous replication solution, and now you're calling it an eventually consistent replication solution. Do you feel at this point, given that your basic deployment topology is 6 VMs and all traffic at one time is going to one of them, do you feel like Galera was a good choice looking back? Is it actually delivering what you hoped for?
Yeah.
And if you were to do that again, do you think you would end up choosing Galera again to do this?
I would say that's a very good question, because I think you also asked the same question, right? Why not use a master and slave? Because in one of the technologies we looked at, that MHA, what it does is it's a master and slave. It basically promotes the slave and demotes the master. And at that time, we thought it's too much chaos, but Galera already has everything in sync, so why not just use it? But you're right, like at this time, if you ask me after like 2 years of experiencing this in the cloud, I would say I would at least give a good thought on why I should not be using, or we should not be using an MHA or a master-slave configuration.
Yeah, I think this Galera is great technology that makes a lot of sense if you can kind of plan the application around it. If you know that
Yeah.
you can use some of these variables and you can design things to send writes and reads different places.
Yeah.
It makes tons of sense.
Right.
Well, we're out of time.
Cool.
So thank you.
Thank you.